Welcome back to the session.
Good afternoon, everyone. Can you hear me?
Hello, can you hear us?
Hello, yes,
Yes,
we hear you.
Okay, okay.
Welcome. Afternoon session.
Did you get a good break previously? Okay, I got the the message in the WhatsApp group. I think that someone having a problem. Mr. Amal, I think, can you please type it again into the chat box because Professor Suejit can see this because he is not in our WhatsApp. So can you please type your problem that you're facing and you have the problem so Dr. Suejit can help us.
Or I'm not sure whether you can also share the screen so that I can have a look at your codings as well. It would be nice if you can share your screen. Okay. So I'll stop sharing the screen, and can you share the screen if you have any problem before we move on in the afternoon section?
Okay, anyone want to share your screen that, okay, your success or you're having a problem? So Professor Suejit can fix it. Can you please share the screen? Because right now we allow everybody to share your screen.
Hello.
Hello, Mr. Woody.
Yes, so my problem is not about sharing the screen. I didn't have power earlier. I downloaded the application yesterday. So I joined an hour later with my phone. So I was just in the class. I didn't go through anything. I was just watching you do everything without understanding anything. So later I probably have to watch the video.
I see, surely. Basically, we have recorded the session. If you
Yes, yeah.
miss the morning session, you can also go back to the material that we did together in the morning.
Yeah.
I think it would be quite challenging to, understand if you don't do it yourself, seriously, because this is more practical session. If you have time after the installation of all the software, you should be attempting how to do this at home. Okay, right. I'll move on to the afternoon session then. So let me share my screen again. So this is where we left off before going for lunch. Let me hide all the black boxes. Yeah. And you should be able to see my screen. Okay, let's move on. So in the morning, we have done the training and validation. So in the afternoon, what we're going to do, we're going to test the data using the test data set. You remember in the morning, we have separated the data set into two sets. The first set is the training data set, and the second set is the test data set. So for the training data set, we have 6,800 rows for 0 and 6,800 rows for 1. And for the test data set, what we have is we have 84,700 rows for the 0 cases or non-diabetic cases, and 1,500 rows for case number 1, which is the diabetic patients. Okay, as I said to you in the morning, for the training, I would like it to be unbiased representation, and also, in other words, unbiased, you can consider this as balanced data set. Okay, in order to have balanced data set, you would have the same number of entries for each class. And for the test data set, it doesn't matter. We can take like quite different number like this, like 84,700 rows for 0 and 1,700 rows for 1. And then we're going to test this. And of course, we need to do some weighting factor later on, but I'll show you how to do it. So what we have to do, because we did the K4 validation, we need to retrain it first. Otherwise, we would be able to calculate the test dataset because all the models have been trained it again. I want to retrain this so that I have the original training model. So copy this back again, and we're going to evaluate this with the training dataset. Okay, so basically this, I run this, and then that should be okay. And then after this, we're going to compute confusion matrices. Okay, for the test dataset, firstly, using the test dataset, and then we compute the confusion matrix. Okay. So I'm going to cut this and place this in the software. So from this row, you remember we need to be able to compute performance metrics, including accuracy, specificity, precision, recall, F1 score. So we place this in the command box here. Okay, and we run this. We're going to have, as you can see, the difference is we have to normalize. This is not normalizing the confusion matrix. Why do we have to normalize? Because the number in each cases are different. Because for the test dataset, we have the number of rows of 84,700 for 0 and 1,700 rows for 1. We need to normalize them in order to make it a relative number. Okay, and so that we can calculate the weighting factors fairly. Okay, so we run this. So that is the percentage in for the logistic regression model for classification. Accuracy is 89.37 and precision is 88.92, recall 89.94, F1 score 89.43, and specificity is 88.79, and the decision tree, so it's quite good, 87.97, 87.72, 88.29, 88.01, 87.62, okay, 91.07, and etc. Okay, so from this point, I would like you to open an Excel file, right? I want another list. Okay, we have different model number. Model number, okay. Model name. Let's type it in to keep it for record first. I think we doing how many models? I cannot remember exactly. Probably 9, isn't it? Okay, and model name. Okay, let's have a look. So we have logistic regression. What else? What is the second model that we have? We have decision tree. What else do we have? We have random forest. Gradient boosting. What else? ADA boost. Support vector machine. Okay, is that it? support vector machine. SVM. So have Adabus and then support vector machine. What else do we have? KNN, K nearest neighbors. What are these? These are the models names that we did together in the morning, naive Bayes. These are statistical models. And neural network. So we did 9 model in total.
Alo.
Apa?
Iya.
Hmm.
Apa?
Hmm.
Apa?
Hmm.
Hmm.
Memang kau dia dah maju eh.
Betul ni make rasa.
Oh.
Iya. Terus sekarang itu kembali yang boleh.
We have done validation using several methods, if you remember. So validation, the first method that we did was resub loss, resubstitutional loss. I just write in short form, it's called resub loss. For the resub loss parameter that we did calculate in the morning was accuracy. You remember? Accuracy. What else? Precision, specificity, precision we call F1 score, right? So let me go back to what we did in the morning together again. I'm trying my best to go slow. I want you all to ensure this is for the training dataset and this is logistic models. These are the numbers. Okay. I just place it here for my record. Accuracy, precision. What else? Parameter is recall and then F1 score and then specificity. Okay, good. So we have the number of 0.8838, 0.8864, 0.8803, 0.8833, 0.8872. And for the decision tree, these are the numbers. So we have 0.9992, 100, 0.9984, 0.9992, and then 1000. Okay, random forest. I will do just a few in order to ensure you understand everything. I will not fill out every models because it will take really long time. But I want you to understand what is the meaning of the model overfitting and underfitting of the model. So that is validation using resub loss. Okay. What else did we compute in the morning? Do you remember? We did compute ROC curves as well for the I won't copy everything. I just want the ROC curve. AUC of ROC. AUC. Again, this is validation. Validation. But this is AUC area under curve of ROC curve. Area under curve. So what was the value? The first one was 0.0 9.9606. 0.9606. The second was 1. The next one, again 1. Are you happy? I want to do only the first 3 models. I don't want to waste my time do all this, okay? And then the second method that we did to validate this is called K4 validation of K4 loss. K4 of 5, K4 of 5. You can try to do K4 of 10 as well. And also in K4 of 5, you will have identical parameters. Are you happy? Are you with me? Yeah. So you have exactly the same. Why do we have to compare between the K4, 5 and also compare the validation using resub loss? Because in K4 cost validation, it will give you the sense of performance of noise, whether the data contain any noise. Okay. So in K4, let me go to K4 of 5. You can try to do all the same thing for all the models. I want the average value for the first one, the logistic model. The accuracy is 0.8835. As can you see these two numbers? If you compare them, are they similar? The answer is yes, they're very similar. What does it say to you then? It said this model, it does not affected much by the noise embedded in the information. So the logistic model is quite persistent to noise in this information. Okay, 0.8860, 0.8831, and hang on, 0.88, or did I skip it one? Yep, I skipped it one row. Okay, accuracy. So I have accuracy, precision, 8835, 8806, 8803, and 0.8831, 0.8866. Okay, what can you tell about these two? I will highlight this to ensure you understand everything. So the first one that is coming from the validation from the training data set, and there are two types of validation method here: resub loss and K4 loss. Are you with me? Yeah. As can you see, these are very similar. Yeah. The performance doesn't affect much. Can you see this? They're very similar. Precision here compared to here. Recall of here. Actually, recall here. Identical to recall here. That is very good sign. F1 score very similar. Specificity, yeah, very similar. 0.88. Okay. And then lastly, ROC plot. Oh, I want to do decision trees as well. Okay, in decision tree, this is 0.728, and then 0.8758, 0.872, so it's 0.688. Am I correct? Yeah. Point 688, and then 0.723. What else? 0.8768. Okay, perfect. Can you see the difference between the decision tree, if you use validation, like Lee sub-loss validation, compared to K4 validation, can you see they very different? Yeah, they're very different. The performance is like worrying performance. What does it mean then? This decision tree model is not tolerate to the noise inside the training data set. Are you with me? Yes or no? Is that clear to you? The first one, the logistic is, although the decision tree, the numbers here look very nice, but in reality, when there is a persist of noise or the presence of noise, the model doesn't perform quite reasonably well compared to the average value. Okay, when the presence of noise, as you can see, the numbers are quite different. Whereas logistic model seems to perform consistently. Okay, let's look at the last one. You can look at all the models by yourself, but I'm going to just look at some of these rather than all of these. Okay. Let me blow it up a bit. Okay, that is 0.8, 0.982, 0.8944, 0.3031, 0.8987, and then last row is 0.8934. Okay, again, similar story to the decision tree. Performance is quite different. If you compare this, they are quite different. Okay. The last thing that we should look at is the AUC of the validation using K4 cost validation that we did together in the morning. So we have the first one, 9603. You see, they similar to each other. The two numbers that I have just highlighted, they are similar to each other. Whereas for the second model, the decision tree, 8738, they're very bad though compared to the Lee sub-loss, which means they not tolerate to noise. They cannot give the real reflection, 0.9704. Okay, 3% difference from here to here. So I would trust logistic model more than the others in this sense, okay? Because at the presence of noise, they can tolerate it. And then the next thing that you should do, you should build up exactly the same table. However, for test dataset, so what does test dataset do? It provides the response for an unseen data, completely unseen data. In other words, you test the trained model for generalization. Student, give me a second, please. Okay, sorry about this. Right. So let me highlight this with this color, and I will need to compute all these numbers again. Test data set. For K4. So can you imagine what we're about to do in the afternoon? Of course, we will do exactly this. Okay, we're going to do Lee sub-loss test dataset. Okay. Where is it? Where is the number of Lee sub-loss tested? We just did a moment ago, didn't we? Here we go. This is the Lee sub-loss test dataset that we just did together a moment ago for test dataset. So these are the numbers for test dataset. So we're going to copy, put it in there. 0.8937, 0.8892, 0.8994, 0.43, and 0.8879. Okay. That is our first model, logistic model. So we can copy this as well. Next, we can copy the decision tree. For the decision tree, these are the number 0.8797, 0.8772, 0.8829, 0.8801, 0.8764. Okay, before we highlight it in any color, let's make it black first. And the last model. Are you aware that actually we have to do all the 9 models, but I'll just show you some example due to the limited time. Okay, I'll show you how to make sense of all these numbers. Because if you can compute everything, but you don't know what do they mean, that is really useless. That's why I want to ensure you can interpret all these numbers. Any question? Is that all right? Are you all with me? Or am I going too fast? Or are you okay? Can you make this table by yourself? Yes or no? Is that everything all right there? I'm trying my best to go slow. Am I going too fast? Let me know. I guess I'm going okay. Right. So can you see something? The performance here compared to this box, you remember this is for training and validation, and this is for testing. Look at the number, they're very similar. Okay, very similar. 0.8838 and 0.8937. The performance difference is within 1%. Yeah, am I correct? This less within 1%, and this even less than like a fraction of percent, even less than 1%, and this 1 and a bit percent, 1.9%, almost 2%. Yeah, and this 89, so this is 1% bigger, 1.1% bigger, and specificity almost identical. Okay, there are words that you need to understand. The first word that I want you to understand is called overfitting. Over, what does it mean by over? Overclaim, overstate, what does it mean? It means when you do the real thing, it doesn't meet the requirement. It's called overclaim, overfitting. Okay, which means when you train the model, it gives you so nice number like this one. Look at this decision tree, 0.9992. But look at decision tree, decision tree when you use it for real, it drop it down a lot. Am I correct? It drop it down to 87.97. And this is called the decision tree model is an overfitting model. Is that clear? This is called overfitting. Okay, and overfitting means training performance matrix. Matrix is higher than the test dataset, test performance metric, test case performance. Okay, and underfitting is just literally opposite. Underfitting means the performance is lower. So when you test it, you will test it using test data set, and you found out it's actually better. But I cannot see anything that with underfitting at the moment. This, you can say this is slightly underfitting. Like logistic model, if you compare this number to this number, you will see that this number is greater than this number, almost 1%. But I would say 1% is not bad at all. Okay, and the last word that we want, optimal fitting. We want this. Optimal fitting, like, normally people talking about plus minus 2.5%. So within 5%, I would say plus minus 2.5%. Do you understand the word? It would be within the difference of the performance matrices, should be within 5%. Like this is actually quite optimal though. This is optimal performance. It's okay. This is sort of okay within one. This is almost 2%. Okay. Do you understand this? So that is within plus minus of plus sign and minus sign of 2.5%. So that is the trick that people use. I don't know why people is so obsessed with 5% in science, but we treat it like this, okay, within 5%. The thing is, so as you see here, this is not bad at all compared to the performance above. But let me finish this. We need ROCs as well. So the rest of the code is of course for the ROC curve. Let me go to the ROC. And this is to plot the ROC. Okay. The last bit is to plot the ROC. Here we go. So we have 0.9652. And for the second model, 0.8801. And the third one, 0.9757. 0.9787. Oh, 0.98757. Okay, that's it. Can you see? And this is even ROC. This is still quite very good. The difference is within less than 1%. Whereas this is having like 12% difference. This is overfitting. And this is again slightly overfitting by 2.5%. Okay, so this is the way you read this table. Okay, but what I haven't done in the code is do 5-4 cross validation for the test data set. I'll show you in the next code, but I want to move on to do some other things now. Okay, let's move on to the next lab. Are you ready? I'll send you some file. And again, can you create another folder? I'll click.
Sorry, can I please also send the files on WhatsApp? Thank you.
Sorry,
On the
say,
WhatsApp group. Thank you. Yes.
no. Okay. So let's just write down lab 2. We're going to look at multiple classification. So you will have more than 2 classes. We're talking about 3 or 4 classes. You have to deal with this differently from the 1 class. Okay. So from 2 classes, multiple classes classification. Just create a folder. You can just write lab 2, for example. Okay, multiple class classification. I will send you some file so you can have a look and we can make a start. Okay. I'll send you 2 files. I need a chat box. Professor Sunny, can you also send this to the WeChat of the student group, please? Thank you. I'm sending it. I think it will be appearing to the chat soon. Yep. For anyone who has got the, yep, yes, that 2 files. Yeah. Okay. So what I want you to do is I want you to put the Excel file right into your lab 2 folder. Just put it in there, like what I did here. Okay, and then open up the file that I've just given you. Multiple class classification. Yep. And then we go back to, are you ready? Have you obtained the file? Are we good? Can I start or you want me to wait a little bit?
Please wait a little bit until you get it on WhatsApp because I'm using 2 devices.
Okay, I'll wait a bit. Okay. Once you're ready,
Yes.
please ensure that you
Okay.
have everything ready. Okay.
Okay.
So I think I have done with this code. I'm going to close this down. One good thing about Jupyter Notebook is you can type it in like this is your first exercise. Let's say first program. Okay. And it will be renamed. You can close it down. You can close it. Okay. Yep. I have closed it, but I still have the main page for the Jupyter Notebook. One of the good thing is I can open this file at any time. Okay. Once I click open the file that we did together, one good thing about Jupyter Notebook is it saved everything that you did. You don't have to recompile. You see, it saved all the results. You don't have to compute anything again. They're all in there, as you see. It's good, isn't it? So everything is saved in the file. So you don't have to recompile everything and wait for another 15 minutes, but everything is safe. So you can retrieve all the information. This is one thing I love about Jupyter Notebook. Otherwise, you need to recompile everything again. Okay, then let me move on to the second lab. So you then go to the folder that you have just created, lab 2, okay, with the CSV file, the Excel file. And then we click new Python 3. And here we go. We have got the empty window, and I'm going to open the text files that I have just given you. This is the codes that we can just copy and paste it. So let's have a look at the data first of the data that we will compute. We will analyze. So is maternal health risk, whether this expected matter will have the normal risk or high risk. So you have the data of age, systolic blood pressure, diastolic blood pressure, BS, and then what else? Body temperature, and then heart rate, and then risk level. Okay, if we look at this risk level, this is our label. We want to create a machine learning model to predict the risk status. So what I'll do, I'll look at the number of cases here first. Let's sort them from A to Z. So you have high risk. How many high risk cases? Let's have a look. You have 272 high risk cases. 272. How many low risk? How many medium risk? Low risk. How many of them? Oh, by the way, the data that we analyzing. So these two data, they are real data from real patient. Okay, obtained it from an open source website called CatGo. And for low risk, there are 406 low risk. And lastly, is it the last type? I think so. Medium risk, mid risk. How many mid risk? 336. So the original data contain, this is the original data. And this is the second is. What we want to do is we want to create an unbiased or balanced data. How do we create balanced data here? You look at the lowest number. What cases is the lowest number? The answer is high risk is the lowest number. So what you have got to do is change everything to the lowest number, which is 272. 272. If you want to change things to 272, what does it mean? It means you remove zero rows from the high risk, and you have to remove how many rows from the mid risk? 336 minus 2372, which give you 336 minus 272. That should give you 64 rows that you need to remove. And then last case, the row risk, you have got to remove how many rows? It will be 406 minus 272, and that gives you 406 272, 134 rows. And that what we will do. And after this, we have to split them into training data set and validation or test data set. This is our plan. Okay. Now we have 272. In this 272, how many percent did I use? Let me check. How many percent? Oh, I used 0.15%, 15%, which means the training will be 95, so 85%, and this will be 15%. So, okay, let me calculate it. 275.85, 131, I think. It will be 131, 231. Okay, of high risk. And 231, 232 around here, 231 mid risk. And lastly, 231 of low risk. And for the test data set, what you have is you have the leftover 2.15 around 41. So 41 high risk. And then 41 that you have separated, but you can add the removed it row, the 64 row here. That 64 rows coming from the they removed it. Are you all right? Are you okay? So we take this, so 41 plus 64, that will be 105 rows of mid risk. And we have 41 plus 134 rows for the, so 41, 105 of mid risk. And lastly, 41 plus 134, that gives you 175 rows of low risk. This is our plan of what we will do. Okay, original data set, we create balanced data set using undersampling method. We have training data set and test data set. So let's copy this into the data. The first part is to import relevant libraries. Okay, so let's just do it. Place and then run it. That's it, done. And the next one, so my computer is running at the moment. How do I know it's running? Because it has this star shape here. Okay, it's done, computed. And then the second type is this. I'm going to use like data frame, CSV reader, open up the maternal health risk file and read out the first few rows. Row number 0 to row number 4, so 5 rows. And this is the data of 5 rows. So you have age, systolic blood pressure, diastolic blood pressure, BS, body temp, heart rate, and this is a risk level. Okay, next. We're going to look at how the data look like using the describe command. Enter. So the mean value of the age is around 30, standard deviation 13.47, and min Q1, Q2, quartile 3, and maximum is 70. And systolic blood pressures as well, and diastolic blood pressure, BS, body temp, and the heart rate. And this is how you look at the data. And the next, data.info Let's have a look. Okay, run it. If you look at the data type, is there any object type? Age, number, integer, number, systolic number, BS, float, number, body temp, float, and again number, heart rate, another number, and risk level. For risk level, it doesn't matter. It is the class type. This is the label, so we don't have to convert this object type. That should be fine. Okay. Next. And we need to check for the missing data, if there is any missing data. Okay, we can look at missing data. Do we have any missing data in this data? No, not at all. In the edge, there is no missing data. In the systolic blood pressure, no missing data. Diastolic pressure, BS, no missing data. Okay, so everything is ready. Let's move on. Then, if you have missing data, you can use this row, but we don't have it. But never mind, in case you have it in the future, I have written some command for you to at least drop the row with missing data. Enter. But we don't have it. But I just given you the code to ensure you can really use the code to work on your own research or your own project. And this is to check again whether it's contain any missing data. The answer is no. Okay, next. Check whether the data is an imbalanced data set. I just count the risk level and count the label. How many of each label? Let's count it. So for the low risk, 406, mid risk, 336, high risk, 272. So this data set is an imbalanced data set, which we have to deal with the data set to make them balance. What do? Is we separate data set into separate classes based on the risk level. So low risk, mid risk, high risk. So we get the data out into subclasses. Okay. And then we split each label. I want to split the low case, the low one. Split the low case. Okay. By how many percent? The low case. Split it out. Okay. 3, 4, 3 rows. Let's have a look. Okay, we use this command. Split each label. We split what? We split the low case. The low case is basically this. We split 406 by 33%. 33% of 406 is around 104. You see, 33% of 106 is 314 because we need to remove 314 rows. As you can see here, this is our plan. Okay, that's why I come up with the splitting ratio of 33%. So that gives you 314 row. And after the splitting, this should give you 272 rows. And another part, the part B will be 134 rows. So let's have a look. This is after the splitting. You see, there is 272 rows. And we can look at part B as well, that we split it out. Part B has got, it must be 134 rows in part B. You see, 134 rows. So We did it correctly in terms of splitting the data out. Very nice. Then, not only splitting the low risk, we have to split the mid risk. We splitting the mid risk in terms of how many percent. We started off with 336, but I said in the code I split it out 19%. Where did I get this number from? I'll show you. 336, 19% of 336 is around 64. Okay, so I want to take out 64 rows. You see that is why I put 19 there. Okay, so I did do this with the, I'll do this with the splitting function at 19%. I split what? I split the data matrix into matrix part A, matrix part B. So this will be 64 row in part B. Okay, and how many rows in part A? The answer is 272 in part A. So I'll run this. You see, in part A, there is 272 rows. And let's have a look at the part B. Run it again, 64 rows, as we expected. That is correct, 64, 272. And high risk, do we have to do anything with high risk? No, not really. Not really. So we don't have to worry about the high risk, because high risk, we don't have to split anything. Then we put them together as balanced data set using concat function, concatenating function. You take in high, mid, low, part A of mid, part A of low together, and a high risk. Okay, then let's move on. And then that is the balanced data set. Oops, this is a repeated code. Sorry. I'll take this. Yeah, the same thing. Okay. And I click describe. Okay. So there are 816 rows. Is it correct? If I have 272 multiplied by 3, 816 rows in total. Is that correct? We should have 8. Yes, that's perfectly fine. We have 816 rows. The next thing, check whether the data set still imbalanced. We then use the same function, but we do it for the balanced data. Let's have a look whether our data that we think it is perfectly balanced will be really balanced. So check that with the risk level 272, 272, 272, perfect. So this is an unbiased data set, which can be used to train the train machine learning models. Okay, let's move on. And then for this, what we're going to do now, we have completed the first part. We have the balanced data set. What we have to do next is we have to prepare for the training and testing. For the training, we were going to split 85% out. So let's do this. Split at 15. Okay, so 85 and 15%. 85%, 15%. Done. Then let's move on. And then we count in the train how many data in the train, how many rows. Let's have a look. The answer is 231, 231, and 231. Perfect, is it? Is that what we want? The training data set has 231, 231, and 231. So this is correct. And then what we have to do, we need to prepare for the test set. The test set, you have data test, okay, that you have split it a moment ago. And the part B that you haven't used, because you remember you separated the midweeks into two parts, part A and part B, and also row weeks into two parts, which is part A and part B. You're going to use the bit from part B and connect them up to the test data set. And again, this make the test data set become imbalanced. But this is completely okay to get test data set unbalanced. It would be fine. Okay. Right. But for the training, things must be balanced. So the test data set consists of 3 to 1 rows in total. Is that correct? Let's have a look. So we need 41, 105, 175. Let's calculate it. So 41 plus 105 plus 175, 3 to 1 rows. So that is correct. So we need 3 to 1 rows. Okay, let's move on and check whether it is imbalanced for test data set. Yes, it must be, because that's what we intended. It must be imbalanced. So we have 175 row rigs and mid rigs, 105 and 41 high rigs. Is that correct? Is that what we want? What we have planned it? Yes or no? 41, 105, 175. Perfect. This is what we have planned it in advance. Next, we're going to do normalization. You remember that we have to normalize for badหมดแล้ว right. Sorry about this. My microphone has run out of the battery. My battery is flat. Right. So let's move on. So we're looking at the set score transformation. We only apply the set score transformation to the X, not the Y. Y is the label, which is the risk factor for maternity period. Okay, risk factor during the maternity period. Okay, let's run this. So we have 693 rows for the training and 321 rows for the test. And then what we're going to do, we're going to use again the same set of classification learner. This is exactly the same as the previous session. Okay, so this is the import libraries, and these are the classifier that we're going to use. So run that. That's it. And then we then train this. Train networks. It will take shorter time than the morning section because the number of entries here are so small, like 300 rows or 600 rows should be very fast. Shouldn't take that long. Okay. Yep, it's completed with warning. It said for the neural network, it has not converged yet, but never mind, I will not config this at the moment. And then we're going to do exactly the same thing. There are two types of validations. The first one called resub loss. The second is cross validation or K4 loss. And the last one not covered here. I don't care about this. Okay. We're going to do resub loss and K4 loss for the validation. So let's do the resub loss first. So you substitute everything in and compute the confusion matrix. Firstly, we do confusion matrix. And then secondly, after the confusion matrix, we calculate accuracy, precision, recall, F1 score. As you can see, one parameter is missing. You see, we only calculate accuracy, precision, recall, F1 score. One parameter missing is specificity. Specificity is not so common in multiple classes. So for multiple classes case that you're doing, you don't have to calculate specificity. Okay, how can you say specific to something because you have so many things? Does it make sense? Yeah. So the next thing is we're going to copy this and compute confusion matrix. Okay, not bad. The first is logistic regression, but the last row is quite bad though. The second, oh, this is quite good. This is okay. This is not bad. Thirdly, okay, this is okay. This is very bad though, 70, 67, yeah? This is quite bad. Okay, and these are the output. Is it completed? Yep, it is. Right, the next one, from this confusion matrices, we're going to compute the performance matrix. Okay, performance matrix. Let's go. Okay, just copy and place this code in there. You should be able to compute accuracy, precision, recall, F1 score. For this code, I use built-in command. I didn't compute it from true positive to negative, but I use the built-in command in Python package. Okay, precision, recall, F1 score support. Okay, and this is it. So you can have accuracy, precision, recall, F1 score. So what I'll do the same thing. I'll fill out the table. Let me remove everything. So what do we have? We have accuracy, precision, recall, F1 score, and you don't need to calculate specificity. So we're going to remove this column because, as I said, it's not so common for multi-classes. Okay. This is 0.6392, 0.6360, 0.6392, 0.6364. Yep. And then the second row, these are the numbers. Point 9278, 0.9277, 0.9278, 0.9273, and the last model, isn't the third model, random forest, isn't it? Yep, random forest. So these are the numbers. So the numbers are 9278, 9276, 9278, 9274. Okay. Next model. Now, 0.831, 0.8825, 0.8831, 0.8827. Next, doubles. Point 6869, 0.729, 6869.6929, and then SVM you have 0.7302, 0.7372, 0.7302, 0.7194. Next, K neighbors. Point 7850, 0.7864, 0.7850, 0.7856. Next, naive Bayes. It would be 0.6 or 46, 0.6129, 0.6046, 0.5847. And the last model is the neural network model. 0.78, 0.2878, 0.7277, 0.7287, 0.7171. Okay, that's it for the validation using K4, sorry, Lee sub loss. The next thing that we will do, we're going to compute the ROC plot from the confusion matrices that we calculated. So we copied this part of code, put it in here, and then run it. You're going to see the ROC plot with the AUC numbers. But it is interesting to note that in binary classes, you only have one number for ROC, for AUC. But for the Lee sub loss, sorry, for the, what's it? For the multiple classes, you will have the numbers exactly the same as the model that you calculate. Okay, so these are the AUC values. Is that clear to you? I think it's clear enough, isn't it? Is it okay? I think it's all right, hopefully. So it follow high risk, low risk, and mid risk, high, mid, low. The way I organize this is not low, high. It will be high, low, mid, high, low, mid, high, low, mid. So which means AUC, you have 3 values of AUC. So you have to insert rows. And this is AUC high, AUC mid. Is it high, low, mid, or high, mid, low? Look at the sequence of this. High, low, mid, high, low, mid, high, low, mid. Okay. You see, for AUC, you have 3 classes. If you have 9 classes, you will have 9 AUC values. Okay, and this is coming from the Lee sub loss, and we're going to fill out these numbers as well. Okay, let's have a look. So the first model, logistic model, these are the 3 numbers. No, not really work like this. Okay. I just want numbers. Okay. Next, the second model, decision tree. As I said, the better to get closer to the corner, so it better to get close to 1. Okay. Next, random forest. Just copy each part will be quicker, isn't it? No, 918. Nine eight six eight 9868. Okay, next, gradient boosting. You will have three AUC values because you have got 3 classes. Then ADA boost. This is very bad. It's less than even 0.5. What does it mean by less than 0.5? It's random guess would be even better. You know, less than 0.5. Very bad model. Next. Okay. Do we have more? 3 more? It's a bit boring, but I want you to understand, so bear with me. Because this is the real thing that I normally do when I do machine learning anyway. Because you must be able to interpret of what is going on. Then the next number. Okay. And then the last model. If you would want to classify 8 classes, you have 8 numbers come out from the AUC values. Okay, that's it. From here, you will not be able to tell much because you don't have you can compare between these and you can say, oh, the best one might be around here. Probably decision tree might be the best model at the moment. Okay, and second best might be this one, and the third best probably this. So this 3 from this table, this is what you can conclude at the moment. But is it really working? You need to probably check the K4 loss as well to see whether how it perform with the noise performance. So I will need to expand this. Let me expand this. Okay. So we're going to compute this table, which is K4 of 5. In some paper, they also compute K4 more than 5 as well, if they want to really check whether things work properly. Okay, right, perfect. Like sometimes they also compare K4 10s as well, whether they're similar to K4 5. But in this study, I'm going to compare K4 5 for one time. The next will be the K4 of 5. So we're going to calculate the average value. So copy it up to this. I'm going to just record the average value of 5 models. K4 5 means 5 models. Let's calculate it. And this is logistic regression. So that will be 56248. Oops. The font will be Tomahawk 11. Just be consistent. Oh, is it Tahoma 11? The whole thing here. Tahoma 11. Okay, right. So 0.6248, 0.617. 7 what? 77. And then 0.62. 0.6248, 0.6163, and then the next decision tree 0.6864, 0.7942, 0.7864, 0.7854. Next, random forest. 0.7893, 0.7932, 793, 7890. Next, practice the practice top and the top one as well. I don't do copies. Okay, it will be all right. Don't worry. I know this is the first time that you do this in your life. I'm aware that it might be challenging, but as you see, I'm trying my best to go slow, as long as you can make sense of these numbers. Okay, is that still okay? Yeah. It's all right. Then the next. Okay, next one. What's wrong with this? This is a number. 0.516. It should go together. Yep, that's fine. Then next. Why can't it go to the right? It should, okay, be fine. Next, we're going to look at the next model. SVM. Point 7042, 0.7073, 0.7042, 0.6941. And next. Point 6133, 0.6138, 0.6133, 0.6118. Is 5825. And the last model, neural network. Okay, before we move on, just look at these numbers compared to these numbers. Is there any row that performs similarly? I think the first one having similar performance, isn't it? The first row. Yeah. Second row is completely nonsense now. As you can see, decision tree, when you test it using resub loss validated resub loss, it gives you almost 93%. But when you test it with K4, which means it's not tolerate to noise, it went down to 78%. And again, 93, it went down to 78%. 88 went down to 78. Okay, and this went down to 0.6. This is not that bad for this model. Okay, it went down to within 3% for SVM. Can you see here? Compared to here. It within 5%, I believe, this thing. Okay, and this is still quite bad. So an okay model to my eyes would be, I would say this is okay. What else? But percent is very low. Percentage of accuracy is low. It's okay, but not as good. Which one is the best out of SVM? I believe this is my number one candidate at the moment. Okay. And this one is okay. Percentage is still high. I then need to look at the test data later as well. If the test data perform well, I will choose that. Okay, this is also good candidate, but need to prove that the test data looks fine. So yellow light. Okay. I love this. Okay, that's fine. Let's move on to the AUC. I need the next bit of code to plot the AUC curve. Calculate ROC. So we can't. Sorry, did you say anything? So the next, I will calculate ROC curve. When you compute things, you have to make sense of it. Otherwise, it will be quite useless. Yeah. So 0.9, let me put it in the calculator. The first model. Excel, where is it? Here we go. Make it small first. I just want to write down, type in these numbers. 0.9158, 0.8304, 0.6738. Next row. 0.9443, 0.8476, 0.8312. Next. Random forest. 0.9753, 0.9215, 0.8832. Next. 9725, 9123, 0.843. Next will be 0.9310, 0.8671, 0.4644. Next 0.9507, 0.8555, 0.7826, 0.9328, 0.8502, 0.7513, 0.8970, 0.8133, 0.6440. The last is 0.9552, 0.8514, 0.7432. Okay, perfect. This is what we have done. Let's look at the last three numbers. I believe in this, right? 9, 5. Are they similar? Are these similar? So the answer is yes, they're very close to each other. Yeah, these three columns are closer to each other, which is very nice, which means they have consistent performance regardless of the noise. And the next thing, we should test it with the test dataset using resub loss. Okay. We do exactly the same. It's fun, isn't it? Do you like it? Or you feel painful? I know you love it. Machine learning is fun, isn't it? It's all about data, all about numbers. Right, this is what we will do. We will fill out this table again to see whether the test performance similar to the validation performance. Okay, next, we validate using test dataset. We do exactly the same and compute the confusion matrix first. Okay, let's go. We run. So these are the confusion matrices. This doesn't work quite well, the first one. This, it looks okay, not that bad, sorry. Because we haven't normalized it yet. We have to normalize when we compute the weighting factor. Okay, after this, we then compute the confusion matrix using weighting factor, using weighted average. So it take into account the different numbers of cases as well. Okay. Run. So here we go. Accuracy, weighting factor. Can I just put this number here? Is it easy? Yeah, yes, that's easy. That might be quicker if we do it this way. So 0.5857, 0.5819, 0.5857, 0.5793. So 93. Then next, 0.8116, 0.7975, 0.7998. Oops, I forgot the first one. Sorry. That would be, the first is 0.7975. Yep, that's correct. Next one, 0.8287, 0.8361, 0.8287, 0.8302. Next, 0.8002, 0.7944, 0.7953. Did I miss a low? Yes, I did. The first is this is gradient boosting. That's correct. Okay, the first is 0.7944, 0.8002, 0.7944, 0.7953. Next, ADA boost 0.6729, 0.7015, 0.6729, 0.6802, 0.6916, 0.6800, 0.6916, 0.6730, and then we have 0.6791, 0.6982, 0.6791, 0.6834, 0.6386, 0.6101, 0.6386, 0.6084, last one, 0.6655, 0.6729. No, I skipped it one row, is it? Didn't. Okay. 0.6729, 0.6655, 0.6729, and lastly 0.6623. Okay, by the look of this alone, what can you tell? We look at the logistic first. So the performance was off by 7%, let's say. So it's very bad though. Okay, we can then kill this. I don't want this anymore because after the test performance it went off a lot. Decision tree, too far off. No, not a good thing. And compare this to random forest, 10% error. So this is all overfitting. This is all overfit. How do I know it's overfitting? Because the performance of the train is a lot better than the test. It's called overclaim, overfitting. Gradient boosting, 9%, still very bad. I don't trust this. ADA boost, okay, acceptable, but number is really low, 68, but it's acceptable performance. I love it, but I put really light green, really light green. Okay, and the next one, 73, it's 4% error, so acceptable within 5. So I still like it. Okay, with the best number so far at the moment. Okay, within 5% around there, yeah, it's acceptable. Let's say within 5, yes, stay within 5. Then K neighbor, the K neighbor is 7, 8, and hang on. My brain is not working properly. I need calculator. H5 minus 16791, 10%. So no. Naive Bay. It's okay, but the number is really low, isn't it? You see, you cannot just trust some high numbers and report it. You have to really check. You need to really validate it. Otherwise, how can you claim that your model is good enough? You need test set and a neural network. Quite consistent within 5%, I would say. No, this is 6%, so that cross out. So we only have a few options. ADA boost, SVM, naive Bayes. Okay, then let's just plot this out. So the next function is to check AUC. Okay. AUC. Yep. Point 9036, 0.7653, 0.6043, 0.9401, 0.8815, 0.8773. But in fact, we won't look at this anyway, so we can skip it, okay? Just look at the thing that we want to look at, Adabus, to check. I want to go on to some other things. So, and SVM, we can pass SVM. Next, we can pass the next ones as well. Okay, perfect. That's done. Okay, we're going to look at this naive Bayes. Naive. Oh, not this one. Sorry. I filled up in the wrong row. So I need the next one. Naive Bayes. Yep. Point 8970. 0.7539. 0.6238. Okay, done. So let's look at Adabus alone. 948. This is bad though. This is bad. And this is 10%. So Adabus is not a good model for me anymore. Go away. SVM 9594, perfect. Oh, this is still within 5%, and that is passed. Okay, SVN pass of my test. So I will put a green flag there. Perfect. Naive Bay. So SVN put a green flag there. So that should be all right. Performance is consistent, as you see. They are all consistent. Naive Bay. 9. That is okay. That is you. 5%, almost, yeah, almost fail, but pass, I think. 2874 minus 0.7539. Oh no, it didn't pass, did it? Didn't pass. 7, did I calculate it? 784,775. Yeah, it didn't pass. So therefore, based on my criteria, I normally remove this as well. So in this test, if I want to employ this, the only model I would like to employ would be SVM. Although the percentage is not the highest percentage, but it's giving you the consistent performance. Okay, I would like to ask you to try to do this by modifying my code for the test dataset. Do it by yourself, okay? So you learn something. Is that okay if I leave you doing this? I want to go on doing some other things that is more interesting. Yeah. Okay, now let's go to lab 3. Are you ready? Any question? Okay, good, perfect. Still, seriously, do you understand me? I try my best to go very slow. Is it far too slow? Yes, that's fine. Very good. I know it's boring. When I did it myself the first time, it was like dead sleep, seriously. But you know, you obtain the knowledge. That is all the point, that I need to spend quite amount of time on just like filling numbers in order to ensure that you just don't trust the number, you test it, you validate it, and then you select the model that you believe. Okay, next one. Let's talk about regression. Again, build a folder. Say lab 3 regression. Do you remember what is regression, by the way? Regression is to predict numbers on a number or numbers. Regression. So lab 3 regression. I just put the date in because I did so many of these exercise so often when I teach my student. So I put in order to avoid redundancy. So I'll give you some file first. Bear with me. Where is my code? Should be here. Lab 3. Not this. Hang on. Regression, surely. Regression. Okay. The file that we're going to look at together is slide location. This file. Okay, I'll send it to you. But I have lost the code. Bear with me. Lab 3. Lab 3. There we go. Okay. Yep, my file is here. Where did I save that? Lab 3. Oh, it's here in front of the desktop. Oh, okay. Right, I can then send the file to you. Oh, where is the chat? And this is very interesting task here. I'll explain the data set, and this is again data set from the real sector. Okay. Hopefully we can do 2 more exercise until you got bored. Right. So this is the code that I have submitted to you, and I'm waiting for the Excel file. Okay, you must have received it. Okay, let me open up the Excel file. Lab 3. Slide location. Yep, perfect. Lab 3. Okay, let's have a look at this file. This is from CT scan. One of the issue of CT scan is that once it obtained the CT scan from the patient bodies, you can have like several slices. Am I correct? Yeah. So how do you locate which organs that you're looking at from the CT scan? Or is there any machine learning model that can read the CT scan and say, oh, this must be the scalp, this must be the chest, must be the abdomen. And this is the machine learning that does that. Okay. And basically I'm opening a big file. Okay. Patient ID. When you see things like patient ID, I would normally remove it. Okay. Why is that? Because This cannot be used as predictor. It cannot be used at all. Doesn't make any sense. Otherwise, if you can predict like sickness from ID, what you have to do today is go to your mobile phone shop and change your number and change your national ID number. If you know ID number can tell whether you're sick or not. I normally remove it. I don't care about it anymore. Okay, remove the ID number. Okay, let me check whether I did the thing in the code. Did I remove the ID number? Oh, I did in the code. I didn't do it in the Excel. I did in my code. Okay, never mind. Let's just explore it further. So that is basically histogram value and the angle of rotation. And they have histogram pixels, like where is the most histogram values. And then the label is this. This is the height from the ground. 0 is the foot, and 150 or 160 is the top on the head. So they try to locate the position, okay, from the toe to the head of which slices they're looking at. Do you understand me? Are you with me? Are you happy? Yeah. You with me? Yes. Hopefully. Okay. You over like you are in pain and you're shocking. But I'm teaching you for real and very much in detail. And I know it's probably no. Do you understand this, or you want me to go over this again for the new data set before we move on? Do you know CT scanning? It's basically medical imaging that basically slides the patient. So taking image in the cross-sectional direction, so you can have stacks. Yes. Okay. We know. Yes. Cool. Okay. And this material is basically the histogram. Do you understand the word histogram? So they try to identify the intensity of each frequency of the pixel. So basically it is frequency related, okay, of the value, basically gradient. Okay, how many gradients starting from 0 to 255, isn't it? So more than 255, so more than 8 bits. Okay, so it's 383 levels, and this is reference height of the patient. So where is the cross section plane? Okay, so what I'll do, I'll start off with the code. So yes, cool. New. I'll close this down, and I'll start to do the new code. So from desktop, lab 3 today, and new Python 3. It's running. Here we go. Right, and then I'm going to open up the text file. So again, we do exactly the same. We read in the regression. The library, we import all the relevant libraries. Here we go, run it. Should be okay, easy, simple. Okay, then we open up the slides location file. Read the data table. And plot the first 5 rows. So how does it look like? It has got patient ID, value 0, up to values 383 and the reference height. And of course, we're going to use this for predicting the numbers, right? So the output will be numbers, because this is a regression model. And then describe. We're going to check whether there is an non-numeric variable. Everything looks okay. Next, this is the standard deviation. How many rows? 5, 3, 5, 0, 0 rows. Next, data info, whether there is anything non-numerical in there. So everything is fine. It's just float and integer, so looks fine. Next. Check the missing data. So then we check the missing bits. Is there anything missing? The answer is no, nothing missing. Cool. Next. In case if there is anything missing, we drop the rows that has contained the missing data out. But you don't need this. But never mind, just type it in for your in case you're going to use it for real. If you have anything missing, so you can check it. Next. Check for missing data again. Hopefully it contains no. Okay, no missing data. Next. We apply one hot encoding, but do we have to do this? Do we have to do this? In here, we don't have to apply one hot encoding. Why? Because everything they are all numerical data, so one hot encoding is not needed. But we should remove the patient ID. Because do you know why patient ID cannot be used as a predictor? Because it doesn't make any sense to include ID number or telephone number or address in the prediction. Otherwise, what you're telling us is living in this house number has caused some sickness, and that is impossible. So we remove the patient ID. And then describe again. Now we should have no patient ID column. Okay. Let's move on. You see, started off from value 0, no patient ID anymore. Perfect. And for regression, you have to check whether the data is balanced. It is good to look at data distribution. Okay. So what do we do? I'm going to sort the label using a sort value command. Okay. And then after the sorting, I'm going to plot the output after the sorting. Because similar to classification, you now want balanced numbers. Okay. You want to train every ranges at the same amount. But can it be true? Oh, in fact, this is not bad at all. And an ideal data would be a straight line. What does it mean by straight line? You have one value, one time, cover all the range. But here, at the extreme end, really little amount at the extreme end. That is quite normal for normal distribution of human. The extreme ends, like the highest value to the lowest value, you probably don't have much information. But I'm going to leave with this. I'm not going to like fiddle with the data anymore. But in reality, you might be able to just remove some of this and remove some of this. Index number 1, so little value, and the last index contains so little values, but I'll take it first. Okay, it doesn't affect much with my training because most of the distribution look okay. It look almost a straight line to me, so that is fine. Okay, next. We're going to separate the input and the output. Okay, input is X, output of the label is Y. Okay, so we have X, we have Y. And then we're going to split the data into 80 and 70%. 80 for the train, 20 for the test. Here we go. Okay, we got train and test. What have we haven't done? We haven't normalized. Okay, we haven't normalized the value. So what I have to do before we move on, let's check the distribution of train and test. The distribution of train and test should be similar. Otherwise, it will be quite difficult to test with the same range. I'm going to just plot the train, the value of the train. Oops. Oh, okay. Forgot this. That will do. Here we go. So this is the distribution of the train, almost starting from 0, and it goes up to almost 100. Okay. For the test, do we have the same distribution? For the test value, sort it and plot the test. I want them to be within the same range. Yes. So from 0 to 100. So the train and the test, they are within the same range. So that is nice. Next, we're going to normalize, apply normalization. Again, one hot encoding. Apply, normalize using the train and apply to the test. Okay. And also, you need to normalize the labels as well. Okay, but let me do normalize the input first before we normalize the label or the output. Okay, we normalize the input. So the training has the length of 42,800 rows, and then the test has got 10,700 rows. And then we're going to normalize the label. Okay, and this is the way to normalize the label. And we check the length as well. It must be the same length as the test. Done. The same length. Yep, perfectly fine. Then let's move on. I'm going to plot the distribution of the normalized data to show you. I'm going to plot the train. So from the scale of 0 to 1, if you normalize it correctly, you should see that the distribution changes to around +3 to -3. -2, yes, correct. Because it has been normalized and the central value should be around 0. And this is called Z-score transformation. Okay. And this is the way to look at the data. So it normalized around 0. And we're going to look at the test data, whether they have the same distribution. Let's have a look. It should be the same. So -2 to 2.5, I think, almost. -2 to almost 2.5. Yep, that's correct. So your input, so your output after normalization, it looks the same for the two cases. And then the next thing, I'm going to declare the models that we will train. And this is to declare models. Okay, for this one, for random forest regressor and support vector regressor, I have commented out. The reason is quite simple. I commented them out because they take too long to run in this practical session. Okay, but if you have time, you can just uncomment it and run it all together. Oh, by the way, are you aware that commenting sign in Python is sharp sign? Okay, so if you want to run it, you uncomment it. But I don't want to wait. Okay, and then we can run this. Oops. Bear with me. Give me a second, please. Sorry about this. Okay. Right. Next, what we're going to do next is we're going to do the same process. So we do Lee sub loss and then followed by K4 loss, the same method in validation. Okay. But, okay, let's put it in first. And then let's see how can we compute this. Okay. So we're going to fit the model using the Y trended scale. So basically take all the Y values in. Oops, I forgot the sharp sign again. It's running. So basically computing by resubstituting the training data set back into the trained models and to get the predictions and compare the predicted results with the original data set to compare whether they're the same or they're different. Okay, it is running. How do you feel? You feel good? You learned a lot today in one day. Amazing, isn't it? Oh, this is like the whole semester. Oh, but it's much more than this. This is like the first 3 weeks, I think, within 2 days. Mm. So the next thing that we should do is we need to compute performance matrix. Okay, the thing is, this is not classification. You don't have true positive, true negative, false positive, false negative, right? But you have numbers. How do you compare numbers? Very easy. You use like error. Do you know error? Any type of error? The first type is called mean square error. What does it mean by mean square error? You calculate the error first and then square it and then calculate the mean. Okay, so you have the label, the known number and the predicted results from the model, and you find the error. How can you find the error? Subtract them, and then what do? Square them up, square them, and then find the mean. How can you find the mean value? Sum them up and divide it by n. So what is this? In reality, what is this? Sum of xi minus x bar square over n. What is it? It's called variance or sigma square. So MSE or mean square error is sigma square or variance. So this only gives you the positive number, which greater than 0. It cannot be less than 0. It's greater than or equal 0. So basically this is error. So error, the lower, the better. Okay, and this has got the unit in unit square. Okay, this is slice location in centimeters. Therefore, the unit of MSE will be centimeter square. And the next one, RMSE. RMSE stands for root mean square error. So you compute the error first and then square them, find the mean value and take a square root. So basically exactly the same, but you take the square root number, which is identical to standard deviation or sigma. So standard deviation or root mean square error must be greater than or equal to 0. And again, the lower, the better. So the relationship between MSE and RMSE is literally square of each other. Okay, and this is the unit of power of 1. So we calculating in centimeter, it will be centimeter unit in RMSE. And the third one is called MAE. MAE stands for mean absolute error. So no square, but we use absolute sign instead. So it will be sum of absolute error divided by n. N is the number of rows. So MAE must be greater than or equal to 0. Again, lower the better. And it has got the unit of 1, so, power of 1. So this is again in centimeter. And the next one is called R value or correlation coefficient. Okay, or R. R is within the range of -1 to 1. Okay, correlation coefficients. -1 means completely opposite. It means like, have you come across of like a man or a lady went to a casino for gambling, okay, and the guy or the lady always lose the bet? What would you do if you know that this lady or this guy will always lose the bet? You just go opposite, bet opposite to him or her. You get the money. Am I correct? Yeah. So in fact, completely opposite is a good thing. Okay, you just do something opposite to this thing. Okay, 0 means no correlation at all. No correlation. 1 means perfectly positive correlation. So it's stick together. The higher, the better. This is unitless. Okay, number 4. Number 5, R square. What is R square? This is square of the correlation or the R value. We just take it square. It's called coefficient of determination or R square value. The R square value is within the range of 0 to 1. Okay, again, higher the better, unitless as well. So these are the 5 parameters that people normally compute. Okay, let's just do the least sub loss. I'm going to copy everything and calculate least sub loss with the results of R square, mean square error, MAE, and everything, right? Let's go. This running. Is it fun? Do you learn a lot today? Or your brain is about to explode? Oh, already exploded. Okay. Hopefully you're all right. Very good. You're trying your best to understand. Very nice. But do you understand? The question is, do you understand? I think it's all right. I go quite slow. Seriously, is there anyone still follow and still understand everything that I have been saying? No one? Oh, is there anyone that really understand my class? I know that you have to practice that, so I recommended you to go over this lecture note again, like in the video, and you should be able to understand everything. Okay, so from here you will see numbers. Okay, linear regression. This is MSE R square MAE. You remember mean square error, the lower the better. R square higher the better. Mean square error, lower the better. Okay, and then you can compare them. So again, you have to get the table ready. So I'm going to copy the table and put it for regression. The regression is not the same as the classification. So firstly, the model name that we can do. So we have linear regression. What else? Ridge regression. And the parameters here as well, remove everything. Okay, linear regression, ledge regression, lasso regression, elastic net, decision tree, decision tree, and then k nearest neighbor regressor, and then light GBM regressor, and then oh, I just did 7 because I commented out 2 of them. Okay, perfect. And the parameters that I'm comparing, what I am comparing parameters, I have MSE R square MAE, MSE R square MSE. Okay, so that is enough, I think. So we comparing these 3 parameters. Okay. Right. From this code, you can copy these values in there. For the first one, $67.733. I just round it to 2 digits. That will do. 0.8642. And then the last one is 6.09. And then for the range, I'll make it Joe skin so I can copy it quicker. For the range, what do I have? 67.73, 0.8642, 6.09. Next, for the lasso regression is not good at all. The error is very high. And R square 0. 0 means, what does it mean by 0? No correlation. Okay. It doesn't work at all. And elastic net 476.706.71, then if I round it up, and then no 0.0, that's correct. 0.044, and then 18.40, and then this decision regressor. Oh, interesting. MSE of 0, perfect, no error, and 1, R square 1, perfect correlation, and no absolute error. Wow, this thing is too good to be true. Let's have a look. We will check. Then 0.09, really low error though. I love this. Okay, very tiny error. 0.9998 R square. That is very close to 1. And 0.8 0.03, and then light GMB 46319, and then 0.9907 and 1.45. Okay, perfect. Hopefully you still understand me. And then you see this bigger better, this and MSE lower the better, and MSE lower the better as well. Oh no, the last one is MAE, not MSE. MAE mean absolute error. MAE. Okay. And the next thing, what we're going to do, we're going to plot relevant plots that involve in the regression. The first is called plot of 2y data. So you have predicted and the label. So you plot them against each other to see whether they correlate with each other. So let's have a look. The first one, what is this model? Linear regressor. So it's sort of aligned within the range, right? Can you see here? It's aligned, it's almost snap, but not as good. Okay, compared to this is still has big error at the beginning. And this one, the one lasso, has no correlation. You see, it's just like a flat line. The predictor is become a flat line, no results. And this one as well, elastic, doesn't work properly, almost zero, almost no correlation. Whereas, look at this 3 model, almost like, I think it's synapted perfectly well in every point, which means the blue and the orange line, they are on the same point, which perfectly fine. And the next one, is it running? Yes, it's running. Okay, we have to wait. Okay, the next graph has come up. This is K nearest neighbor, which is not bad at all. Some missing data coming out. Okay, some errors here. And this is light GMB. Still bad, but not as bad. Okay. So this is the first type of plot. Let's go on to the second type of plot. Oh, okay. Light GMB. Okay. Yep, I'll check it for you. In some of you who probably learn this for the first time might be struggling with this line, I think. Okay, let me show you how to fix this. You can create one of the box here and anywhere in your code. Okay, type in pip hit install. It means install this package like GMB and then run it. Python will install this package for you. Sometimes when you just newly install the package, it doesn't come with this package, so you have to install it. So if it highlight any line that say error, you don't have the package. What you can do, you just copy it, the package that you don't have. For example, you probably don't have like GMB. You can just type everything in like what I did. Type in pip install like GMB command and then run it. It will take a while to run because here we go. Okay, that will do. After this, can you run the error again? The error should disappear. You should be fine now. Okay. Is that okay? Yeah, I think I have answered your question.
Are you okay?
Are we good?
Yeah. Are you okay, Mr. Madhubashi? Should be okay.
Yeah.
Yeah.
Okay, good. Yes, okay, perfect. So you can, right. So the next one, the next plot, apart from the comparison plot, you can plot residual plots. Residual plots will show you the magnitude of errors on each point. Okay, it's called residue. So we can just put this in and plot residues. This is the residues. Magnitude is around 40 for the first case. The second, again, around 40. And this is the whole lasso, no correlation. So it will be very big error. Again, elastic will be big error. Whereas this decision tree has got very good number, as you can see, almost 0, but there will be like 2 points, I think, only 2 points that has some error. Only 2 points on the curve. Very interesting. Okay, very nice response. Okay, is it running or is it completed? It's running. Okay, another curve coming up. Oh, okay. This is very good. K nearest neighbor. As you can see, most of the errors snapped it around 0, but few points go more than negative 20 for the residue. Okay, interesting. LGM is good. Okay, then this is residue plot. After the residue plot, next plot that you should be able to do is called scatter plot. Show the scattering of the information. Okay, so for the scatter plot, what you want to see that the data align well in the diagonal direction. Let me show you what do I mean by align well at the diagonal direction. You want to see everything snaps to this diagonal line. So the better it goes to the diagonal line, it means it's perfectly matched. This is no matching at all. There's no matching at all. And this step within very well for the decision tree. This is very nice. I'm waiting for the next model to show up. It will take a while. Okay. This is K neighbor. Not bad at all. It snaps on the they snap on the diagonal line, but only few points that going out from the diagonal line. Light GMB look like this as well. Very nice. Okay, next. We're going to do K4 cost validation. We're going to calculate the MSE, R square, and MAE. And of course, we have to calculate average value, the mean value. Okay, the mean value of the MAE. Something wrong with this part of the code. Bear with me. Let me open up my previous code. I did mistype it somehow. Let me check the code for you. Okay. This is another data set, not the one that I'm teaching you. Let me close this down. Not this one. Bear with me. I'm trying to find the missing code. Should be this one. Yeah. Okay. Yep. Bear with me. Okay. So I don't think it works, this thing, because I'll show you why. The syntax is very weird. Okay. This is okay. Print mean matrix. Right. Okay. Average NP matrix. Means, is it running? Come on. Error. Where is it? Yep, the line that I said, matrix. So how did I save this in there? Okay, it will print out matrix. Okay. It happened by the name mean matrix. It will be matrix. Hang on. Matrix. Matrix with no S, is it? Error. So that will be, bear with me. I did this somewhere. I just like copy the wrong code and send you. Bear with me. Let's still plot. So we up to here. That is matrix. Where is my code? Here is it. Okay. So it's saved as y4. No, I want matrix. Okay, I want the is go by matrix in matrix, average matrix in matrix. Come on, is it working? Error in this slide. Student, bear with me. Give me a second, please. I'll fix this. I'll debug this. Shouldn't take me long. Bear with me. So we access the matrix by mean matrix. Let me open up the previous code. I need to debug this, and it's quite common when you wrote software. You need to debug things all the time. Bear with me. Average. Okay, matrix name dot matrix. Yep, that's correct. That's double. Okay, that is double array. Okay, that's fine. So that will be name matrix. I think this will work. This will do, I believe. Yeah. So I'm going to change this code and send it to you again. Okay, bear with me. So which part? This part. So that will be okay. I'll send it to you again. Please use this file instead. Otherwise, you have some error. Where is it? Where is the chat? Professor Sunny, can you resend this file to the student? I made some error in the code, so this is the one that I'm sending is about to go, I believe. Hopefully. Yep, it's that. Yep. So that is an error in the command. But after this, as you see, it works fine now. Yeah. So you can just copy the results in here. MSE, oh, huge results. Okay, for huge cannot be used. So I don't care about it. It's like doesn't make any sense. Yeah, but look at this. It's okay for rich. 0.1385, and this is 0.685 and 0.2754. And then the next one, 1001 and minus 0.001. So zero correlation. It still insists on the zero correlation. And the next one, elastic net. Elastic net give you 0.9560, 0.4, 0.0493, 0.8241. And I'm waiting for the code to run. And after elastic net, we have to wait for another 3 rows. Shouldn't take that long. Then we do the test results, and that's it. And that should be the regression. Because of the limited time, I wouldn't be able to do the clustering or unsupervised learning. But if you're interested in doing the unsupervised learning, let me know. I can share some code with you as well. Oh, okay. This is the new version. I'm sending. Yep. Okay, elastic decision tree. Oh, decision tree is not bad at all. As you can see here. And this is the K4 cost validation, 0.0157, 0.98. Oh, not bad at all. Very good. And then this looks okay. I like this. And then K neighbor. Oh, not bad at all as well. 0.0006. And then 0.9994. And then 0.0065. Not bad at all. And then light GMB. Come on. Is it running? Yep, it's running. Almost done, I hope. Yep. And that is the number. That's numbers. 1319869. Not bad at all. 0.0728. So this looks okay. And then what we have to do is we have to then test the data using the test data set that we have separated in advance. Okay, so the next is to do test data set. We do exactly the same and we calculate MSE, MAE, root mean square error, the same thing. Okay, and we calculate the parameters. So we send this in, copy this, put it in. This is the number. So it's computing different models. Yep, it's running. Just take time. It will take a while, but it will be completed. So we calculating these rows for the test data set. But by the look of this, I quite like the last 3 rows, the last 3 models. Okay, we have got the number. For linear regressor is 68.1596. Actually, we don't have to type this in the tool because we don't care about the first 3 rows. But if you have time, type this in for for good practice. So a good model would be decision tree. Let's have a look. Started from 4.8467 and 0.9904. 4155. When you use it for the test data set, as you can see, this has higher error. Okay, higher error, which means this has over fitting performance. But it's still all right, 99 point less than 1%. I would be happy with this. K neighbor. Point 0.0865 and 0.9998, 0.01141. Very interesting. For this one, for the first parameter, it has under fitting performance, not overfitting. Because when you use it for real, it's better. This is the same performance, exactly the same performance. And this is under fitting. So this is all right, still in the good range. And the last one, 6.4191, and then 0.9872, 1.6115. So they have got similar performance as well. I quite like this. Okay, that's cool. As you can see, these three models, if you compare them, clearly the best is K neighbor. This is the best at the moment. Okay, look at the performance, low error, high R square, low MAE error. And then what we're going to do, of course, we're going to, okay, we can plot, but I will skip this part so you can do it yourself. I'm going to go for, I didn't do the, the K4 cross validation. I'll leave it for you to do. Okay, you can modify my code to compute this part for the test dataset. And this is the plot for the test dataset. No correlation, no correlation. For the decision tree, this is not that bad, as you see. But for the K nearest neighbor, this is very good. Snap very well to the axis. This is not bad at all. Okay. And you can plot residue plot and the scattering plot as well. Scattering plot. Shouldn't take you long to compute. And the last piece of the code as well, so that we can call it a day today. The scatter plot. I'll leave some tasks to you for at least you try to fill up this table. So you do K4 cross validation. You can follow the example above. It will be the same code. Okay, shouldn't take you long to do. So in fact, 3 is not bad, but I think K nearest neighbor is the best in this case for the test dataset. So I think that's it for today then. Do you have any question that you want to ask me at all?
Are you guys still there? Finally, Professor Suejit, okay, finish his training. If anyone has questions, please feel free, or you still stuck in some process, so please share to us. Maybe right now you are still following the steps, but don't worry, because we're gonna have the recordings. So you can practice by yourself, and I will upload the recorder as soon as possible within today. So you can, catch up on the practice today.
Okay, if there's no question.
Do you have any questions, or you still stuck on something? So today was like a very intensive course practice. As we already informed you, normally it will be like 2-3 weeks for the students, but today we wrap up within 2 days because our limitation of the time. However, I think that it's very useful for you guys for the updated knowledge for the biomedical engineers to know the AI, because nowadays everybody talks about the AI, and not only for the the disease diagnosis, but you can apply this knowledge for in your working department, like for the medical devices management that we already informed you. So it is very very useful tools for you guys. So in the case if you still stuck with the programming and have no more questions, so it's okay. So today it's just like full of the day for the practicing, and okay. I hope you're gonna have the enjoy weekend after this. So okay, I'd like to thank you very much to Professor Suejit today for very intensive course and his valuable time to share with us for 2 days. And we really appreciate it because he is a real busy guy nowadays. So this is a very benefit for you guys that our guest speaker share the lecture and also practice and examples on this thing. So thank you, Professor Suejit again, and for you guys, thank you very much.